The expression for sum is none other than our XOR gate, that is A XOR B, followed by our carry is nothing but a AND gate. So the reference expression is A XOR B, then a borrow. The expression will be A dash into B. So we will be getting this combination only when our A value is 0 and the second input B value is 1. Hello everyone, I welcome you all to the first session that's under Unit 4. So yes, we have completed almost 3 units and we are hopping with the Unit 4. This is a last unit of your syllabus that's under Digital Computer Organization. Yes, let me tell you, this is one of a very easiest subject out of your BCA, and the 4th unit is all about, there is combinational as well as sequential logic circuits. Over here, my name is Deepa Kutnikar. I'm working as an assistant professor in the Department of Computer Science, Vidhyaashram, Temple of Excellence, MYSURU. So let's move forward and understand what's the agenda of today's session. In today's session, we'll be discussing about what exactly is combinational logic circuit and what is sequential logic circuit, followed by the difference between the combinational as well as the sequential logic circuit. Up next, we also discuss the adders. Yes, we will be discussing the half adder, full adder, then followed by half subtractor as well as full subtractor. So this is a complete agenda of today's session. So let's move forward and understand what exactly is our sequential as well as combinational logic circuit. Yes, exactly. The combinational logic circuit is a primary logic circuit where we will be providing inputs and will be taking outputs. But here the main point to note is the output is completely dependent on the present states itself. It is not dependent on the past outputs or past inputs, nothing like that. So here under combinational logic circuit, we can say the outputs of the combinational logic circuit, it depends only on the present inputs, but it's not the case with respect to sequential logic circuits. When we speak with respect to sequential logic circuit, there will be multiple sequences. Yes, exactly. And the output is also dependent on the previous input states as well as a present input state. Also, we can say there will be a feedback from our output towards the input. And the second point is, yes, that's the feedback. Regarding feedback, there is no need of feedback with respect to combinational logic circuit because these are basic circuits. But when we go with our sequential logic circuit, there is a need of feedback because it has to track the output, correct? It has to take a part of output and it will be given to the input. So there is a requirement of feedback under sequential logic circuit. Up next is a memory elements. As it is a basic logic circuits, there is no need of memory when we speak with respect to combinational logic circuits. But whenever we go with our sequential logic circuits, yes, absolutely, there is a need of memory. The memory element plays a very vital role under sequential logic circuits. Next one is a clock. There is no need of clock when we speak with respect to combinational logic circuit, but yes, a clock is required whenever we go with a sequential logic circuit. So these are a complete difference between a combinational as well as sequential logic circuits. Up next, let's see we have various combinational logic circuits, and what are those? Yes, starting with a half adder. Always we can't say when we go with a binary logic, we need a complete full adders because full adders a bit of time consuming when compared to our half adders. So there will be some simple circuits where there is a requirement of addition, that too with respect to minimum 2 of the inputs. And those cases we can go directly with the half adder circuits. So yes, this is nothing but a half adder block diagram where it will be having 2 inputs, that is A and B. And whenever we consider addition, then we will be getting 2 words in our minds. The first one is the sum and the second one is carry, right? Yes, absolutely. Even here we use those same words, even with respect to our Boolean algebra or even with respect to combinational logic circuits, we need the same thing. Yeah, over here A and B are the 2 inputs, and S and C is nothing but a sum as well as a carry, which is nothing but 2 of the outputs. This is nothing but a half adder. And let me repeat this thing, like this is a type of combinational logic circuit and it is used to add 2 of the inputs. All right. Up next, let's see a logic diagram as well as a truth table with respect to half adder. So let's complete a logic diagram. But before that, we have to understand like what is the expression for sum and carry. All right. So that's why our sum, the expression for sum is none other than our XOR gate, that is A XOR B, followed by our carry is nothing but a AND gate. So let's draw a simple logic diagram for a half adder. We have 2 of the inputs A and B, followed by the first one. Let's add a XOR gate because XOR gate forms a sum of our half adder, then followed by a simple AND gate. AND gate represents what? Yes, it represents a carry. This is a simple logic diagram by using basic gates, then followed by, let's get back with our truth table. As we are dealing with 2 of the inputs that are A and B, we will be having 4 combinations, right? That is 0, 0, 1, 1 followed by 0, 1, 0, 1. Yes, it's done. Next, for sum, what is the expression? So, the thing is XOR gate. It is A XOR B. So, let's XOR 0 XOR 0 is a 0 and 0 XOR 1 is none other than 1. 1 XOR 0 is a 1. Okay, done. Followed by 1 XOR 1 is a 0. Yes, it's for sum. Followed by carry, it is a AND gate, correct? So yes, what is the AND gate output? Whenever we have 2 of the inputs has 1, at that time our output will be high. So this is a simple truth table with respect to our half adder. So whenever a half adder is asked, you have to first define like what is a half adder, then followed by you have to write a block diagram followed by the expression, then a logic diagram using basic gates for that expression, then you have to draw a simple truth table. So these are the things what you have to represent whenever half adder is asked to you in your internals or your exams. Yes, once we are done with half adder, let's hop with full adder. The difference between half adder and a full adder is here the number of input terms are more. It is not 2, okay? And the output terms, adder. So whenever we spell a adder, we will be coining 2 terms, that is a sum as well as carry, correct? Again, here is the same thing. We will be dealing with 2 of the outputs, that is sum and a carry, and the inputs are A, B and C in. So this will forms our inputs. Great, right? Even here, this is a type of combinational logic circuit which is used to add not 2 numbers or not 2 of the logics, 3 of the logics, okay? And the outputs will be 2. Yes, it is none other than a sum and a carry. But here we are representing carry as C out. Up next, let's get back and understand like what is the expression for our sum and carry. So we know the sum expression for half adder was a XOR gate, right? Even here, it is a 3 input XOR gate, all right? So that's what A XOR B, B XOR C in. Done. Followed by carry. Our carry is none other than A into B plus B into C plus A into C. Okay, so it is like A into B plus B into C plus C into A. Yeah, this is what the carry expression is. Clear? This is a block diagram of full adder where you'll be dealing with 3 of the inputs, that is A, B and C in, followed by 2 of the outputs, sum and the carry. As we are using C at both input end and output end in order not to get confused, so we are specifying the input side as C in and the output side, that is a carry, has C out. Clear? So let's move forward and understand the logic diagram. Yes, as we know, what is a sum? It is a 3 input XOR gate, correct? So you can see here we have A, B and C in and we are representing it in a form of XOR gate. Okay, it's done. Up next, with respect to carry, we have this AND gates and the output will be C out. So yes, this is a complete logic diagram. That's by using basic gates, we are representing the expressions of sum and carry of a full adder. Done? So let's see a truth table with respect to this. So as we are dealing with the three of the inputs, A, B and C in, we will be going with 8 combinations of zeros and ones, then followed by our outputs will be none other than a sum as well as a carry. So now let's see what is the combination of inputs. So yes, it's none other than 4 ones followed by 0011 0011. Next, with respect to C, it is 0101 0101. Okay, so we have completed this. Next, with respect to sum, what is that we have to do? It is none other than XORing, correct? So A XOR B, then B XOR C, right? So 0 XOR 0 is a 0 followed by 0 XOR 0. It's again a 0. Again, 0 XOR 0 is a 0, then 0 XOR 1 is none other than 1. Okay, great. 0 XOR 1, it is a what? 1, correct? Again, 1 XOR 1, sorry, 1 XOR 0 is a 1. 0 XOR 1 is a 1, followed by 1 XOR 1 is a 0. Great. Up next, 1 0 0. So, we are having 1 XOR 0, it is 1, followed by 1 XOR, again a 0 will be a 1. Then 1 XOR 0, it is none other than a 1, followed by 1 XOR 1 will give us a value of 0. Similarly, 1 XOR 1 is a 0. So, 0 XOR 0 gives us a value of 0, followed by 1 XOR 1 is a 0. Then 0 XOR 1 will give us a value of 1. So, this is all about a sum. It's done. Next, let's go with the carry. So, by seeing carry, what we can say here is the combination. By saying first 4 bits, we can say it is a output of AND gate. Correct? A logical AND. Then next 4 bits are giving us a value of OR gate. Right? So yes, it is nothing but a carry with respect to full adder. Yes, this is with respect to full adder. Next, let's go forward and understand like what is a half subtractor. When we have a half adder, at the same time it will be easy and we can complete the things by half of the thing, correct? That's why we can go forward with the half subtractor. Half subtractor is also a type of combinational logic circuit, but here we will be performing subtraction operation of 2 of the inputs and the output will be, yes, what are the outputs when we consider subtraction? It's none other than a difference and a borrow, right? Yeah, let's see a expression for that. So the difference expression is A XOR B, then a borrow. The expression will be A dash into B. So there is a very slight difference with respect to half adder as well as half subtractor. That's with respect to only borrow. Even there, for sum, the expression was A XOR B itself. Yes, even here it's continued the same thing. And the borrow expression is A dash into B. Great. Up next, let's see a quick block diagram representation of a half subtractor. Yes, it is a half subtractor which deals with 2 of the inputs, okay, and then followed by 2 of the outputs. So yes, this is with respect to a half subtractor. Next, let's see a quick logic diagram that's been drawn by using basic gates, then followed by a truth table. So for logic diagram, as we know, the difference is a XOR gate, correct? So we will be drawing 2-bit 2-input XOR gate. All right, the output is a difference, which is none other than A XOR B, followed by our borrow is none other than A dash B, correct? So here we are giving the symbol A and we'll getting A dash. So here we can see the 2 of the inputs will be A dash and a B, and finally the borrow output will be A dash into B. So this is all about a basic logic diagram. Then let's head up with a truth table. As we know, we are dealing with 2 inputs, that is A and B, followed by 2 outputs, that is D and B naught. Now, what are the combinations? So, as we are dealing with 2 inputs, we will be heading with 4 combinations, that is 0, 0, 1, 1 followed by 0, 1, 0, 1. All right, we are done. So let's start with a difference here. What is a difference? It is none other than our XOR gate. So we will be getting 0, 1, 1, 0. So this is a XOR gate output followed by A dash B, correct? So let's see, where do we get this A dash B? So let's see here, the borrow and the answer, that is A dash B, will be getting here. So the A dash, in the sense, this is 0. For 0, we will be calling it as A dash, then followed by B, yes. So only with respect to here, we should get 1 and rest all are zeros. So this is all about our borrow. Any doubts under this? So we will be getting this combination only when our A value is 0 and the second input B value is 1. So this gives us A dash B, correct? All right. This is all about a half subtractor. So next, let's head up with, what is it? Full subtractor. Yes, even here we are heading with full subtractor. Why? Because we are not just dealing with two of the inputs. Sometimes there will be necessary and needs to go with multiple inputs, right? So for that, we will be heading with full subtractor. Even full subtractor is a type of combinational logic circuit, and here we'll be having 3 input bits and 2 output bits. So the 3 input bits are A, B, and then followed by B in. Then the output bits are none other than the difference as well as a borrow. Clear? So this is a basic block diagram of a full subtractor. Now let's see the expression. Expression is very, very important, right? So the expression for our difference is A XOR B XOR B in. Okay, that is nothing but a XOR of input terms. The second output, that is a difference, is all about A dash B plus B into B in plus A dash B. Okay, so this is an expression for borrow. So there is nothing like how this expression will come or how we have derived. These are the standard expressions with respect to the half adder, full adder. So we have to just represent it, write it, and we have to represent it in the form of a logic diagram. That's by using basic gates. Clear? Alright, there should be no confusions like how we got this expression, nothing like this, okay? These are the derived or the standard expressions. There is no derivation for this. So whenever you consider full subtractor, you have to write this expressions directly, like for difference, I'll be getting this, and for borrow, I'll be getting this expression, okay? Alright, let's head up and know the main thing, that is a logic diagram and then a truth table for full subtractor. So starting with a logic diagram. So yes, as we know, it is a 3-bit XOR gate. All right. So first we have got the XOR of 2 of the bits, then followed by we are heading with 1 more bit. That's a third input. Clear? So we will be getting a difference, then followed by our borrow, correct? So for that borrow, we are using complete AND gates. Any doubts on this? So yes, we are using AND gates and followed by a OR gate. Clear? So this is a logical representation of a full subtractor. So now let's head up with a truth table. So as we know, we are having 3 inputs. We will be getting 8 different combinations and 2 outputs, that is a difference and a borrow. So now let's start. As we know, the output is nothing but a XOR gate, correct? XOR gate of our inputs. So you can see here, it's a 0 XOR 0 followed by 0. So our output will be a 0. Then I'm getting a 1. So if you, let me just tell you one more trick over here, that is whenever you have, the trick is only with respect to XOR gate, like whenever you have an odd number of ones, at that time your output will be 1. And whenever you are getting an even number of inputs, at that time the output will be 0. So considering this, let's solve this. Okay, so we are having a 1 only once. It is none other than odd number of 1, so we will be getting a difference 1. So even here 0 1 0, so odd 1, so 1. Up next 0 1 1, so we are getting a even number of ones, that is 2 ones. So what will be our output? It is a 0, correct? Then followed by again 1 0 0. You can observe here it is a odd 1, correct? So I'm getting output 1, then followed by 101, it's a even one, correct? So for that our output is 0 followed by 110. Again my input bit is 2 ones. So I'll be getting a 0 as my output, followed by 1, 2, 3, 3 bits of ones, and the output will be 1 for that. Up next, with respect to the borrows. So you might remember with respect to our full adder, we had written the starting bits as AND gate and next 4 bits for OR gate. Let's see what is the difference here. It's 0010 followed by 1011. So this is with respect to difference, then followed by our borrow. It's nothing but A dash into B. So we have to do that A dash into B, then followed by B into B dash. Then what is it? B into A dash. So if we clear this, we will be getting these values. Is this clear? Or else you can just see and you can make out the difference between the different bit as well as a borrow bit, and it will be easy to understand and learn at that time. Clear? Let's move forward. So here I would like to write a quick keynote which will be very easy and helpful for you people to understand and recall the expressions. So as we saw, that's under our half adder, full adder, half subtractor, then a full subtractor, all are having different expressions for sum as well as carry. So now let's write it each one so that it will be helpful to understand the difference as well as to recall the things whenever it is required. So the first one what we had discussed was a half adder, which will be having two of the outputs, that is a sum and a carry, correct? So what about our sum? Sum was a XOR gate. It is A XOR B, and a carry was a simple AND gate A into B. Clear? Then we had a, okay, so this is done. Let's write a half subtractor together. Half subtractor. So for half subtractor, what we had? We had a difference and a borrow, correct? So the expression for difference was the same thing, that is A XOR B. Then the expression for borrow is, you remember what is it? It is A dash B. Great. Next thing, let's start full adder. So as we know, for full adder, we will be having 3 of the inputs, right? And the output is none other than a sum and a carry. The sum expression is A XOR B XOR C. Considering my inputs are ABC, followed by the carry is A into B plus BC plus CA. Okay, considering our inputs has A, B, C. Clear? Next, what we had, that is a full subtractor. So do you remember what was the next one? It is none other than a full subtractor. So for full subtractor, again we will be having 3 of the inputs and 2 of the outputs, that is a difference and a borrow. So the difference is none other than A XOR B XOR C. Okay, assuming that our input has ABC. Clear? Followed by the borrow. So you can just convey or correlate this borrow with a carry. Wherever you have A, you have to rewrite with a A dash. Clear? So let's start doing that. A dash B plus BC plus CA, but wherever we have A, we will be writing it as A dash. So these are the key things that is very helpful. If you note this, you can just directly write what is half adder, then half subtractor, full adder, full subtractor. So for this, you have to draw the logic diagrams. That's by using basic gates. Then you have to write a truth table by seeing the number of inputs, the number of combinations you have to write. Then the 2 outputs. So yes, the outputs are sum and carry for adder, and it is a difference and borrow for subtractor. So these are the things what we have discussed in this session. So any doubts in this? I believe it is clear to you. So let's see, these are the things that we discuss in our next session. That is, we will be speak regarding flip-flops, then decoders. Also, we will be learning like what is an encoder And under that, we will be learning octal to binary encoders. So these are the things that we discuss in our next sessions. Until then, thank you.